Okay, so this is going to be for, I don't know which homework this is, 26 or 25, something like that. It's the stuff from 9.2 and 9.3. So the first problem is 8c, and we're trying to find when this capital G of xy is continuous. And from the front of the page, from 9.2, I cut and paste this chunk here, which mentions continuity. So continuity just means that in 2D, the continuity means that the limits from the two sides end up being the same, and they equal the value of the function right there, so it fills in the dot too. In 3D, it's the same coming from every direction, and it equals that dot as well. But that's not really the main way that we prove continuity, or that we check for continuity over a set of points. What we do instead is we use the second property, which says sums, differences, products, and quotients of continuous functions, actually also compositions of continuous functions, are also continuous on their domains. So if we break up ln of x squared plus y squared minus 4 and just look at ln of x, that's continuous on its domain, which is x is positive, right? Because remember, ln looks like this. And then if we look at the inside function, well, that's just a polynomial, so it's continuous on domain, and its domain is R2. And so if we combine them, then the new function is continuous on its domain, which should be x squared plus y squared minus 4 has to be positive, which, if we think about it, that's the same thing as x squared plus y squared has to be greater than 4. If we think about the boundary of that in R2, that's x squared plus y squared equals 4. That's radius 2 circle, but it's actually greater than that, so I'm going to do a dotted circle here. Radius is 2. And since it's greater than 4, it's actually everything outside the circle. So we would shade everything outside that circle in the xy plane. And those are the points at which the function is continuous. Okay. So let's take a look. Oh, by the way, in D, if I assign that one later, there's a misprint here. It should say f of x, y, z. So I left off the z by accident. Okay, so let's try the next problem. 9.2, number 9. So use polar coordinates to find this limit. So let's refresh polar. Our cos theta is the same thing as x. Y is r sine theta. And that's all we really need. So this limit is going to turn into the limit. And if x and y are turning into 0, 0, that's the same thing as the radius is turning into 0. And then we've got x cubed, which is r cubed cos cubed. And then y cubed, which is r cubed sine cubed. All over x squared plus y squared. So hold on one second. Okay, sorry. Paused it for a second, so I got to finish this. X squared plus y squared is going to be r squared cos squared theta plus r squared sine squared theta. And if you think about the bottom, if you factor out the r squared, cos squared plus sine squared is just 1. So then this turns into limit as r goes to 0 of r cubed cos cubed theta plus sine cubed theta over r squared cos squared plus sine squared, but that's just 1. And then we can cancel out a couple of r's. And we get the limit as r goes to 0 of r cos cubed theta plus sine cubed theta, which ends up being 0. Okay. All right. So let's take a look at the next one. So the next one, we're finding a fourth order derivative. with respect to x, with respect to x again, then y, then z. Okay, and here's the function, right? Now notice sine is a continuous function, and 3x plus yz is a continuous function. So sine of 3x plus yz is going to be continuous everywhere. And both of the sine functions have continuous derivatives everywhere. So technically, using Clara's theorem or the extension of that, you can actually do these derivatives in any order you want. You could do, if you wanted to, you could do f sub y x z x if for some reason you thought that would be easier. Now, I don't think it really makes a big difference for this problem, but so we'll just do it in the same order that we got them in. So first is f sub x. So f sub x, treat y and z as constants, and x is a variable. So this is going to turn into cosine 3x plus yz, and then times the derivative with respect to x of the inside. That's the chain rule part. So this is going to turn into cosine 3x plus yz times, and then the derivative of this with respect to x, well, yz is a constant then, so that turns into 0, and you're just left with 3. So this is going to be 3 cos 3x plus yz. So then let's take the second derivative, which will be with respect to x. So now I'm taking the derivative of this with respect to x. So that's going to be, let's see, the 3 is a constant in front. Cosine turns into negative sine, so this would be negative 3 sine 3x plus yz, and then times the derivative of the inside with respect to x, which is again 3. So then this turns into negative 9 sine 3x plus yz. So now we got a y. So we'll go f sub x x y. So we're going to take the derivative of this with respect to y. So first the derivative of the main thing. So it'll be negative 9 cos 3x plus yz, and then times the derivative with respect to y of the inside. So that's going to turn into, so now z and x are the constants, so that's going to turn into 0, and yz, the derivative of yz with respect to y is just going to be z. So this is going to turn into negative 9z cos 3x plus yz. Okay. And then we need to take it with respect to z. Okay, now notice this is actually now two things that have, whoops, sorry about that, two things multiplied together that are z terms. So we need to use a product rule. U, v, we're going to turn that into u prime v plus v prime u. Okay, so u prime, and remember these are all with respect to z, so u prime is just going to be negative 9 times v cos 3x plus yz, and then plus v prime with respect to z, so that's going to be negative sine of 3x plus yz, and then we need the chain rule part, so times the derivative of the inside with respect to z, which is just going to be a y, times u, negative 9z. So if we simplify it a little bit, we get negative 9 cos 3x plus yz, and then the negative negative turns into a plus, and then we'll throw the 9yz in front, sine of 3x plus yz. So there it is. And you should get that regardless of the order that you take the derivatives, with respect to whichever variables. Well, you can do them in whatever order you want there. Okay, so let's take a look at the next one. 8, yeah, sorry about that. Okay, So number 8, they give you this contour map, so topological map. So these blue values here are the different heights, or z values, for different points that you plug in on the xy plane. So it says estimate f sub x at 2, 1 and f sub y at 2, 1. Well, let me mark 2, 1, so over 1, 2, up 1. So we're looking right around this point. Now, f of 2, 1 seems pretty clearly 10 to me. It's on that 10 curve there. But that's not the slope in the x direction or the y direction at that point. So when it says what's f sub x at 2, 1, think of it as saying what's df dx when we plug in 2, 1. And I like this notation because, well, that's just what's the change in f over the change in x around the point 2, 1. So you could kind of look at the slope going in the x direction. We're kind of looking at a point over on the left side here and a point over on the right side here. And the question is, what's happening to the slope in the x direction at this time? So it's really like asking, what's f sub 2 minus f sub 1 over x sub 2 minus x sub 1? Or rather, instead of saying f, let's say, what are the z values? Z sub 2 minus z sub 1 over x2 minus x1. Close to 2, 1, assuming that it's a relatively good model. Right? Well, I don't know. Let's say that this is roughly, I don't know, let's make the x value here about 1.2, and the x value here, like, I don't know, 2.6, something like that. And the z values are 8 and 12. So if I go 8 minus 12 over 1.2 minus 2.6, and I've got -4 over -1.4, which is just 4 over 1.4. And then, I don't know, whatever that equals. Let me see. 4 divided by 1.4, about 2.857. So that's the slope. That's how z changes as x changes around the point 2, 1, roughly. Now, I will tell you, the book that I took this from actually does it differently. They figure out what this slope is and what this slope is, and then they average the two. So, although honestly, the answer comes out to be very close still to 2.86. If these numbers were really strangely different from each other for some reason, then you might consider looking at it differently. Okay. So then we also have to look at the y's, f sub y at 2, 1. So that's what's the change in f over the change in y around the point 2, 1. Technically at the point 2, 1, but we're estimating. So I guess I should use that there. Whoop. So this is about, let's see, here's 2, 1 again. And we'll pick this one and this point to help us estimate. So the y value here looks like, I don't know, maybe like 1.9, let's say, and the y value there just looks like 0. And then here are our z values, 10 and 12. So the change in z is 8 to 12. And then the change in the corresponding y values are 1.9 to 0. And so if I work this out, that's -4 over 1.9, which is about -4 divided by 1.9, about -2.105. So that would be the slope in the, well, an estimate of the slope in the y direction. Okay, now I'll tell you, it depends on where you're estimating these y values to be, and if you're using the 8 and the 12, or if you happen to be taking this one and averaging them. So there are lots of different answers you should get, but these are ballpark answers, right? I'd say if you get something in the 2.7 to 3 range for the x, you're probably pretty good, and something from like -2 to -2.2 range, 2.3 range are pretty good. If you did the average, and I think the book that I took this from used 1.8 and then averaged the top and the bottom parts, and they ended up with -2.25 for the slope there. So, okay. Anyway, you get the idea, hopefully. And if you don't, make a mark of it so that we can talk about it later. So let's take a look at 9. So find the, and this one you're only doing A. So find the indicated partial derivative. So let's take the, and we need with respect to x. So y is a constant now. So the derivative of ln is 1 over whatever's on the inside. And then times the derivative of the inside. So that's going to be with respect to x. So that's going to turn into 1 plus, and then this is x squared plus y squared to the half. So that's where we got to do 1/2 x squared plus y squared to the -1/2, and then times the derivative of that inside. So it's the chain rule on crack. So this is 2x here. So let's see, these two's cancel. And then I'm not going to bother simplifying because I can just plug in 3 and 4. So this is going to be 1 over 3 plus the square root of 3 squared plus 4 squared times 1 plus, and then this will be 3 over the square root of 3 squared plus 4 squared. And then 3 squared plus 4 squared is 25, so square root of that's 5. So this would be 1 over 3 plus 5, which is 8, times 1 plus 3 over 5. And if I simplify that a little bit more, it's 1/8 times 8/5. So then these cancel and we get 1/5. Okay. So let's go on. Let's take a look at the next one. Number 10, A and B. 2x plus 5. I didn't realize it was 2x. I thought it was just x. All right. So let's see. A and B for number 10. All right. So 10a, z equals some function that's only in terms of x plus some function that's only in terms of y's. 2 y's for some reason. Okay, so we want, first, the derivative just with respect to x. Well, only that part deals with x, so it's going to be d dx. Well, I'll write it like this. We're basically taking d dx of both sides here. So f of x plus g of 2y is what we're taking the derivative with. Well, this thing here has no x's in it, so that's going to turn into 0. So really it's just df dx. But notice f is a single variable function. It's only in terms of x. So there's no need for the partial derivative here. It's regular df dx. Or you could just write f prime of x because there's only one way to take the derivative if there's only one variable, one dependent variable. Okay. So if we do dz dy, that's going to be d dy of the same function. Well, this one is only in terms of x. So if I try to take the derivative with respect to y, that turns into 0. So really I'm just saying the derivative of this one. So it's going to be dg dy, dg of 2y dy, times the derivative of the inside with respect to y, which is 2. So, and notice g is only in terms of y, so I don't really need the curvy g's. I can just do this, dg of 2y dy times 2. So I'll just put the 2 right there. Or you could write it as g prime of 2y times 2, so the 2 would go in front. So I think that's probably the best way of writing it for this problem. Okay. Part B, I'm not a huge fan of part B, to be honest. We'll try it. So z equals f of 2x plus y. So dz dx is going to be d dx of this function. Well, that's going to be df dx, df of 2x plus y, right, times the derivative of 2x plus y with respect to x, which is 2. So the book I took this from, I'm not a huge fan of this notation. I wrote it like this. And then they noted that this was with respect to x, which I am not a big fan of. I don't even know if that's appropriate, to be honest. So that's that. And then the dz dy would be d dy of the same thing. So that's going to be f prime 2x plus y times the derivative with respect to y of the inside, which is 1. And then you just need to know that f prime 2x plus y, the prime, is with respect to y. So I would say don't worry about this one. We can can that one. So, okay, let's take a look at 11. So Clairaut's theorem. All right. By the way, there's the little blurb about Clairaut. So let's see. U is really a function of x and y. U is a function of x, y equals x to the 4th y cubed minus y to the 4th. And it doesn't actually say verify that the whole theorem holds. It just says verify the conclusion. So here's the conclusion right there. Now we already know that this is a polynomial function, and so all of the derivatives are continuous everywhere, which means Clairaut's theorem has to hold. But we're actually just checking as f of xy equal to f of yx. So in this case, it's u. So let's do u sub x, and we get 4x cubed y cubed. And then if we do u sub xy, then we're going to get, let's see, what's that going to turn to? So x is the constant now, so we get 3y squared out of the y term. So that's going to turn into 3x cubed, oh, sorry, 12x cubed y squared. So there's u of xy. And then if we do u sub y first, we get, let's see, so x to the 4th stays the same, and we get 3y squared. So it's 3x to the 4th y squared minus 4y cubed. And then if I take the derivative of that with respect to x, then this term turns into 0, and I'm left with bringing the 4 down in front, 12x lower the power by 1, and it happens to be exactly the same, which is good. So that verifies the conclusion holds. Okay, and then we got one more here, number 13, Laplace's equation. So Laplace, I don't even know how many different applications this guy was touching in physics, but he does a ton, or he did a ton. And so this one takes the form, the Laplace equation takes the form u sub xx plus u sub yy equals 0. So anything that happens to fall into this pattern, this is not always true, by the way. Anything that happens to fall into that pattern is called a harmonic function, which plays a big role in various physics properties. I don't know if you ever had to study them or not, but they are huge in physics. So show that this is the solution of Laplace's equation, which means show that this works in here. So let's find u sub xx. Right. So first we need u sub x. So u sub x, we got to think of this as, sorry, u is probably not the best. Let's do v and w. So when we take the derivative, it's going to be vw prime plus, oh, actually, we don't have to worry about that. The sine y is a function only of y. So if I'm taking the derivative with respect to x, sine y is treated like a constant. And the derivative of e to the x is just e to the x. So this is just e to the x sine y again. And then when I take the second derivative, same deal. Right? So then let's look at u sub yy, or u sub y first. So the first derivative, e to the x, is now like a constant. So this is going to be negative e to the x cos y, because sine turns into negative cos. And then if I take the second derivative, well, the negative e to the x stays the same, and cosine turns into, oh, sorry, this is still positive. The derivative is cos. I'm doing integrals. Okay, so then the second derivative, now that becomes negative sine, and the e to the x stays the same. And so then if we check to see, does it fit in Laplace's equation? What's u sub xx plus u sub yy? Well, it's e to the sine, or e to the x times sine y, minus e to the x times sine y, which is 0. So it works. And that's that. Hope that helps a little bit, and I'll see you guys soon.